A very good afternoon to everyone, and thank you for joining once again. We are live with a very interesting topic to discuss and talk: the Golden Eye James Webb Space Telescope. The James Webb Space Telescope was launched in December 2021 and released its first image on 12th July 2022. And from that moment, when the first image was released, there was a buzz and excitement amongst all space enthusiasts. So today we'll be discussing and try to understand about JWST. And to talk more on this, we have once again with us Dr. Priya Hassan. Her last session was such well received by all the participants on Career Path, and the video is available on Planetarium YouTube. So, in case you want to refer, please go and check that. So, about Dr. Priya, I would like to share that growing up in Mumbai, Dr. Priya went to USSR to pursue her integrated master's in physics at the Moscow State University, Russia. She did her PhD in astronomy in Osmania University, Hyderabad. She did an Indo-French postdoctoral research project at the Inter-University Center for Astronomy and Astrophysics, Pune, India, and worked as DST Women Scientist at Osmania University from 2006 to 2009. She taught at Mukaffam Jha College of Engineering and Technology, Hyderabad, and joined Maulana Azad National Urdu University later in 2015. Planetarium, thank you, ma'am, for again talking to the all online enthusiasts who really want to explore information about the JWST. So over to you, ma'am.
Thank you, Prerna, and thank you. Good to be back again. And today I'll be talking about the Golden Eye, the James Webb Telescope, which you can see has gold coating on it, hence we call it the Golden Eye. And it's been a lot in the news of late. You must have seen it very often. I hope you can see my screen, right, which I'm sharing.
Uh,
And
yes.
Prerna, is my screen showing? Oh no.
Yes, ma'am, it's
Oh,
coming.
should I share it again?
No, it's coming on the
Okay.
screen.
So, yeah, great. Okay. So James Webb has been a lot in the news, and that's why we thought it was the right time to actually talk about it. So, for example, you can see a Google Doodle over here, which is showing you a nice, friendly James Webb, which has given out the five most well-known first images of James Webb, so a bit about which there's been lots of talk. These were released on the 12th of July, and there's a lot of thing going on about James Webb, and therefore it's very important for to understand what's about this mission and what makes it so very special. Now, the James Webb, what was the idea behind James Webb? It was actually conceived to be a giant leap forward in our quest to understand the universe and our origins. So, the basic idea was to study origins, which would be every phase of origins in the sense from the first luminous glows after the Big Bang to the formation of galaxies, stars, planets to the evolution of our own solar system. So, it was supposed to, it is meant rather to approach the question of origins at all levels. And that's the basic purpose. And for that, James Webb was actually designed to be an infrared space telescope. So I would basically explain to you why was it necessary for James Webb to be an infrared space telescope to actually meet its main purpose, which I told you the main purpose was the study of origins from the study of life, planets, stars, galaxies, as well as the universe, right? So we will now see why did we need to answer this question, why did we need an infrared space telescope? So, first of all, we'll start from the other end. The first important thing, but before that, I'll just tell you a short, I'll just show you something short about Webb's journey. I hope you all are aware that James Webb was launched last year on Christmas in 2021. And this was launched from French Guinea, which is a place called Kourou, which is in South America. And from there, you had this is the telescope being launched. This is using the Ariane rocket. And what you can see is right on top, you can see is where here is where James Webb is there. So we can just pause for a minute and you can now see is that it was a space telescope. I will explain to you why space telescope. But now what you can see is that there's something very interesting about James Webb is that it had to be launched. And while it was launched, James Webb is a 6.5 meter telescope, right? The primary mirror has a size of 6.5 meters. Now, obviously, no rocket will let you put a telescope, a 6.5 meter mirror and launch it in total. And therefore, you see the interesting part about James Webb is it's actually a folded mirror. So you had a 6.5 meter mirror, which is folded. Okay, just imagine. And packed up and put over here so that when it's launched, it gets launched like this. And after the launch, you have the telescope actually opening up, right? So this is the launch which took place, like I told you, on Christmas 2021, 6 months ago. And you see that after the launch, um, this is an animation. You see the fuel rockets actually drop off because the main stuff is this. You do not need these things. So these are called multi-phase rockets, where the rocket throws out its fuel tanks as they get used. So you can see that these side fuel tanks, as the rocket was launched, they actually get thrown off, right? And gradually you have the whole thing opening up in space itself, and it falls into the ocean. So that's why you have all these launch places on the east coast, so that as the earth rotates, this thing goes up and it throws all these parts which it's throwing, they'll go straight into the ocean, right? And what you have over here is the folded telescope. Now the folded telescope is what actually takes off. Finally it further detaches from this thing. You have the final detachment which takes place, and you can see that over here when the flight takes place. I can slightly speeden this up, and so you see this part gets detached, and here you have your telescope going out in space, right? So here you'll see the picture of approximately the last picture that, or the last image that we have of the James Webb. That's the last image we have of the James Webb, which looks something like that. This is an animation. And then what happens is the telescope actually has to open up, right? It has been packaged. So the first thing you can see is what the sun shields, because you need power for the telescope. So first of all, you open the sun shields, sorry, the solar panels. Then you have the sun shields. Now the sun shield is the size of a tennis court. Okay, it's huge, and it's made up of 5 layers. We'll talk about it more in detail, but it's basically to shield the telescope from any kind of radiation. That's because it's in infrared, and all other things are emitters in infrared. The Earth, the Moon, we, all of us. So you need to protect the telescope from any kind of emissions. So you have the sun shield opening up, which actually opens up into 5 layers. Now the mirror you can see is actually opening up. This is the primary mirror, which is gold coated 6.5 meters. The secondary mirror is over here. So you can see that this whole thing actually got deployed. It got opened up. Here's the secondary mirror and here's the primary mirror. And all this happened in space, right? So I just wanted to give you this a glimpse to you, to actually show you how the James Webb in principle is a total engineering marvel, right? Because you have, just imagine you have a telescope which is folded. You fold it and you launch it 6.5 meters, right? And then after it gets launched, then the whole telescope has to open up, self package, open up itself, open the solar panels, open the sun shields, open the primary, open the secondary, and then you needed to do all the alignment of all the mirror, etc., which we'll talk about in a bit. And that took this whole period of 6 months. So you had the telescope being launched in December, but the first images were finally released only on the 12th of June, because it took 6 months for the whole telescope to, assemble itself, align its mirrors, get ready for observations. Now let's go to the first part. So it's a telescope. What is the purpose of a telescope? A telescope basically collects light. So the larger the size of the telescope, the more its light gathering power. And the other thing what the telescope does is it resolves. It gives you details. So when you look at this, you actually get detail. And telescopes have been used in astronomy for the past 400 years. The first to use it was Galileo. And even Galileo, though he did not use a very big telescope, but even with that small telescope of his, he actually discovered things which were very revolutionary. For example, he discovered that there were craters on the moon, and the moon was considered a heavenly body, which was not supposed to have craters and things like that. He actually observed the satellites of Jupiter, which showed that you had objects going around another object other than the Earth. Remember that these were the times of the geocentric model, where it was believed that the Earth was the center of the universe. And when he saw Jupiter with its satellites, he actually saw another system of satellites going around another object. He also saw the phases of Venus, and the phases of Venus could only be explained if Venus has an inner orbit, an orbit inside the Earth's orbit, and only then could you have phases on Venus. And therefore, what he observed was already a threat to the geocentric theory, which was what was being supported by the church at that time, and for which obviously the church was not too very happy with the results which Galileo knows. But we still call him the father of modern science, because he actually did scientific observations which could actually, give you basis for theories. right? So yes, so the first thing is we need a telescope. That's right. Now we'll come to the second point, which is the story about space. Why do we need to take the trouble of sending this telescope in space? Now, many of you all may be aware of the electromagnetic spectrum. Now, the electromagnetic spectrum ranges all wavelengths and all frequencies. So, frequencies, high frequencies are here, low frequencies are here. Similarly, low wavelengths are here and high wavelengths are here. So, you have it ranging from the gamma rays, X rays, ultraviolets, all the way down here, right? But our eyes, they only detect visible light, which lies between 3000 to 8000 angstroms. So, that is the visible light window which our eyes actually see. The problem is that you have the whole electromagnetic spectrum, which is much larger than that, which is very important. And that's because, like I said, visible light is only a small fraction of the electromagnetic spectrum. And there are a whole bunch of physical processes which occur in different wavelengths. For example, if you want to look at some high energy phenomena, you would have to observe it, say, in X rays. If you want to look at cold gas, for example, neutral hydrogen in the galaxy, you will need to look in the radio or in longer wavelengths, and these are not detectable by our eyes, right? So if you want to study different physical processes, you have to study the rest of the electromagnetic spectrum, for example, radio, X-ray, gamma rays, etc. And that's where the problem comes. The problem is because we have our atmosphere. Now, the atmosphere on the earth is life giving. If we didn't have the atmosphere, life would not exist on the earth, because the atmosphere is like a blanket. It protects us from radiation which comes in from space. And therefore, you can see our protective blanket is like this. It is completely opaque for high frequencies, which is, for example, X rays and ultraviolet lights cannot pass through our atmosphere, which is a savior for us, for life on Earth. And therefore it's completely opaque. You just have some windows. This window is in visible light. Then you have some windows in the infrared and microwave. You have a very large window in the radio wavelengths, and then you again have it blocked over here. So what you see is that though we would like to study the electromagnetic spectrum in toto, we cannot from the Earth, because the atmosphere stops these frequencies from coming through us, right? And therefore from the Earth we cannot observe these, and therefore it becomes necessary to observe this to go to space. The other reason for going to space is that, again, the atmosphere actually has turbulence. So if you look at the atmosphere, there could be different layers of gas in the atmosphere which are kind of moving because of turbulence. And hence, if you were looking at a star, the star's position will shift. This is what we call twinkling, right? I have a star over here, and because of these moving, clouds or whatever, turbulence in the atmosphere, the position of the star shifts. And as the position of the star shifts, you look at this image over here. This is the star, the observer looks, the star position shifts, and it shifts so fast that we do not notice the individual images. See the net image. We see the resultant, and the star seems to be taking a bigger size. It kind of gets defocused. It takes a larger size. So this is the twinkling, and if you have a larger object, it takes a larger size. And therefore, what will happen is that when I look at an object, for example, here, this is an image of Jupiter. If I look at it without the atmosphere, it would be clear like this. But if I look at it through the atmosphere, and when I look at Jupiter, because of the turbulence in the atmosphere and these clouds, etc., this thing gets smudged. The light gets smudged. And instead of my seeing a resolved, sharp image of Jupiter, I actually see it in this way, with all these things smudging it and, kind of making it blurry. So you can see this image, for example, over here. If there's a lot of turbulence in the atmosphere, this is the original image which I should see. But now, because of the blurring out, it comes out like this. Similarly, if I were looking at the moon would look blurred like this. But if I could resolve it, right, if I could see it without it, this is with the basic telescope, you remove this blurriness by improving the resolution, then you can see the craters neatly and nicely. Similarly, here there are examples of three different telescopes. This is the HST, the VLT, and the ALT, with improved resolution because of improved size of the telescope. So you are going from 2.4 meters to 10 meters to 30 meters, 38 meters rather. And you can see that you can now resolve and see stars. So the problem again is with the atmosphere, that the atmosphere has turbulence and the atmosphere has different conditions also. Depending upon that, it varies what we call seeing. And this is called seeing, and that causes the errors in what is called astrometry. Astrometry is the measurement of position of objects, which actually gets messed up because of the atmosphere. So you get blurry images as well as you cannot resolve objects because of the atmosphere. So we know that light is a wave, and because of that, it anyway shows diffraction, right? Diffraction is a wave property. And what does diffraction do is if I have a point source of light, it actually spreads the light, right? Instead of you seeing a point source over here, you instead see this ring-like structure where the center part is called the Aries rings, the center one, which is given by 1.22 lambda by d. And what you can see is that because of that, instead of you're seeing a single star, you actually see it smudged, right? And for example, if I have two objects which are close to each other, such that their Aries disks overlap, you cannot resolve them. If we want to resolve them, then the Aries disks have to be separated. Only then can you resolve it as two sources, right? So this effect of diffraction is anyway going to be there. Even when we go into space, this effect will be there. But this is the only effect which is left in space because you don't have an atmosphere. If you have an atmosphere, you have the effect which is because of blurring as well as the wave nature which causes diffraction. So you'll have the double effect which will make it even more blurry, right? But space will minimize it. Now, the other thing which we need is we are going to focus upon infrared because this telescope basically works in the infrared, which are longer wavelengths. So these are shorter wavelengths, gamma rays, X rays, ultraviolet. After visible light, the next wavelength which you get is the infrared wavelength, okay, which is this part, which is essentially from 700 nanometers to 1 millimeter. This was discovered by Herschel around 1800. And I hope all of you are aware that all of us are excellent infrared emitters, and therefore I'll come to that in a bit. Why do we need to do infrared? But essentially this gives us the reason why do we need to go out in space, because if you go out in space you can study different wavelengths which are, for example, X-ray, gamma ray, ultraviolet, and in this case we need infrared. I will just tell you in a bit why do we want infrared. So you will be able to access different wavelengths. The second thing is that you can get actually diffraction limited seeing, in the sense that's just that amount of 1.22 lambda by d, right? And then ground-based telescopes obviously have limited observing time because of the Earth's rotation. So you have the day-night cycle. But for example, space telescopes, you don't have any such problem. You can continue observing. And we'll see that space telescopes, either some of them are what are called survey missions, where their job is to just go on scanning the sky, survey, or they could work as observatories, which are for targets. James Webb is a target, this thing. It's an observatory which will observe targets. It does not do on survey mode. It looks at targets, right? So if you have candidates or targets from other sources, you actually use the James Webb to then look at those target sources. There are obviously disadvantages of space telescopes. The first important one is that space telescopes are basically expensive compared to ground based. You have to make your telescope, launch it, do all those things. The other problem is that because they are out in space, they are difficult to maintain. The Hubble Space Telescope actually had servicing missions, but that's because Hubble is only at a distance of 570 kilometers from the Earth. So going to Hubble is not at all difficult. It's a very easy journey to go there, and hence there were servicing missions for Hubble. Um, but obviously, space telescopes, like for example the James Webb, cannot be serviced because it has been sent to a point which is very far away. So there were various telescopes, which space telescopes, which have been launched, which have been operational. For example, the Chandra telescopes works in X-ray wavelengths, which is still operational. You have the Suzaku telescope, you have SOHO, which observes the sun, you have Kobe, which is for microwave background radiation, you have Hubble over here. There are a whole bunch of space telescopes which have been sent. Spitzer, Kepler, Planck. There are many, many space telescopes. And therefore, we have a good amount of experience in the launch of space telescopes. So let's focus on one of the most well-known space telescopes, which is Hubble. This is the Hubble Space Telescope, and Hubble has actually, revolutionized astronomy. Another telescope which is still operational is called the Chandra. Chandra observes in the X-ray. It's named after the Indian astronomer Chandrasekhar, the Nobel laureate, and it has various instruments on it. It was launched by the space shuttle. It is still very much operational. And if you can see, we have some very excellent images which have been got by Chandra. Like I told you, it basically observes in the X-ray. You can see these different images. So basically in the X-ray, what you're doing is you are observing hot gas, right? So for example, if you look at these different objects, This is a supernova, 1987A. So you had the end stage of the life of a star, which actually threw out a shell, lots of energy, and hence it emits in the X-ray. So you can see that this X-ray emission can be seen with that. This is Eta Carina, which is a very energetic star, the Cartwheel Galaxy, the Helix Nebula, and you can see Messier 82, all these objects over here. And all of them are very interesting objects which have been very well studied using Chandra. And for X-ray, you, like I mentioned, you have to observe in space because you do not get X-rays on the Earth, and the only choice is to observe them like that. Um, Another telescope which is spent out in space, which is called Spitzer. Spitzer it's a smaller telescope. It's only an 85-meter one, but it was specifically meant to observe in the infrared. So it has three basic instruments on it: the IRAC, the IRS, and the MIPS, and it basically observed in a wavelength range from 3.6 to 116 microns. The other infrared telescope which went was Herschel. Herschel has a size of 3.5 meters. Okay, and this basically observes in the far infrared to the sub-millimeter wavelength, and that's the very wavelength in which this is the infrared wavelength where you can study early stars and planet formation, right? Now, the Hubble Space Telescope, we'll come back to it. It has a size of about 2.4 meters, okay? And there are various cameras on it, the NICMOS, the ACS, the WIP-PIC, etc. And it has totally revolutionized astronomy. If you actually see the kind of images that we got with Hubble, this is a longish movie, and hence I'm going to run it at a faster speed because otherwise we won't be able to manage to see it. But I basically want you to see the kind of images, the kind of quality of images which we have actually got using Hubble. Hubble has given us some excellent data about this thing. Hubble basically observed in the optical bands, but along with that, it did a certain amount of even infrared, near infrared. So that's Hubble over here, and this is at a height of 570 meters above the Earth, and you can see that's the telescope, a whole observatory by itself, and we have excellent images taken by Hubble of various astronomical objects. There are various over here. I'm not going to go into these details, but you are most welcome to have a look at videos. There are many videos available on the net of various images that we have got of astronomical objects using Hubble. But like I told you, Hubble basically observed in the optical and in the near infrared. So, yeah. Now, what's the difference with James Webb and Hubble? So, Hubble, like I told you, is a 2.4-meter telescope. James is 6.5 meters, named after a NASA, a very important director in NASA who led the Apollo program, that is Webb, James Webb. And it is an international consortium. It's made up of the United States, Europe, and Canada. And the whole mission has cost not 11, but I think $11 billion, not 10 billion, but 11. And like I told you, the purpose of it was basically to study origins, okay, to study galaxy, star, planet formation in the universe. So basically, the idea was to look back through time when galaxies were young and observe galaxies that are very distant, very young, as well as observe dust clouds where planets and planetary stars and planetary systems form, etc. Now, that was the basic aim of this, to study this. Now, like I told you, Hubble basically observed in the ultraviolet, optical, and near infrared. But Webb, because it's studying origins, it basically needs to observe in the infrared. And I'll tell you why in a minute. Why do we need to look in infrared? But in that way, in principle, Hubble, James Webb is not exactly a successor to Hubble. It's a space telescope, but it's looking at totally different wavelengths compared to Hubble. Hubble was doing ultraviolet, optical, and near infrared, while James Webb actually does mid infrared. And therefore, in principle, you would actually say that it's a successor to Spitzer or even Herschel. It's more of a successor to Herschel or Spitzer rather than a successor to Hubble. We would actually say that. So, what is the expertise required? The most important thing is that if you're observing in infrared, the important thing is that if you want to study star planet origin, this happens in very dusty regions. And if you want to observe in dusty regions, you have to do it in the infrared. Now, the infrared, like I told you, human beings, you, me, the earth, the moon, we are very good infrared emitters. And therefore, it becomes very important to protect the mirror from infrared emission from any other bodies. And therefore, the telescope has to have one. Number one is the mirror, the 6.5-meter telescope, which NASA made itself, as well as the sunshade. The sunshade was also made by NASA. ESA, the European Space Agency, took up the job of the rocket. The launch was that's an ESA center from which it was launched, as well as the which actually cost the launch cost it's $1 million. And MIRI is one of the mid-infrared instruments which is there on the telescope, which has been totally developed by the European Space Agency. Canada actually worked on the robotic arms. They have expertise on robotic arms on the space station, as well as they have made a camera on it, also called the NIRIS camera. And the total cost of the telescope is about $11 billion, of which 1 billion was on the launch. So, like I mentioned to you, you have a big difference in the mirror 2.4 to 6.5, and that basically increases the collecting area. So, the collecting area goes by pi d squared, right, which is rather pi r squared, the area of the mirror. So, it goes as the square. So, if you're going from 2.4 to 6.5, you're almost tripling it. But in terms of the area, you're doing 3 squared. You're almost going, much more times than the area of Hubble. So, it actually gives you a much more, you can look at much fainter sources. Again, if we compare the two, Hubble was actually launched at a height of about 570 kilometers, while James Webb has been positioned because it's an infrared telescope. We don't want heat to come from the Earth and the Moon onto it. So we sent it off to a further location, which is called the Lagrange point L2, which is at a distance of 1.5 million kilometers. It's quite far from the Earth, right? And the other thing is that, James, like I told you, Hubble is only 2.4, James Webb is 6.5 meters. Now, making a single 6.5-meter telescope is very, very difficult, and therefore it's made up of what is called a honeycomb design. Okay, so it's made up of segments. You have totally 18 segments, and these segments are made up of beryllium, and the segments join up together to give you the mirror. The other problem with James Webb is that because it is at 1.5 million kilometers, it's too fast to be far to be serviced by the Earth. While Hubble actually could be serviced, for James Webb it would be very difficult to think about servicing it. And so, therefore, what happens is if you see that in the telescope, the mirror and the instruments are not enclosed in a tube. In Hubble, they were in a tube. Here, you need it to be open so that the telescope is cooled. So, it's very important to cool the telescope because it's observing in infrared light. Both of them are observing visible also infrared, and both use solar panels, right? Now, let us come to I was to explain to you why are we going in for infrared. One thing I told you was that for stars and planets formation, the region where stars and planets are formed are very dusty regions. And in dusty regions, you do not get light in shorter wavelengths because the light will get absorbed. But if you actually look at longer wavelengths, you can actually observe it. So if you want to see dusty regions, you have to see it, for example, in the infrared. So for looking for very young stars or planets, we have to look in the infrared. The other reason is now for the origin of the universe. Let's look at that. Most of you must have heard about Edwin Hubble and his discovery of the expanding universe. So, what did Edwin Hubble do? He basically used this is the Mount Wilson telescope, and he used this to basically study galaxies to get the spectra of galaxies. Okay, and when he got the spectra of galaxies, he actually I'll talk about that. He used something called the Doppler effect, right? What was the Doppler effect? The Doppler effect is that supposing I have a source of light or any waves, sound waves, light waves, etc. If the source is going away from me, then the waves kind of get stretched. And if they get stretched, they move to a longer wavelength, which is redder wavelength. If the source is coming towards me, the waves actually get pushed and they get pushed, and therefore the wavelength reduces, it comes to the blue part. And therefore, red shifted objects are moving away from me, while blue shifted are moving towards me. And therefore, if I observe the spectrum of a source and I can identify what is the shift or the delta lambda in the spectral line, I can get the velocity of the source. And that's what Hubble did. So, for every galaxy he observed, using the Doppler effect, he got the velocity to the galaxy, of the galaxy. The second thing he did is he measured the distance to that galaxy. And he used that using something called Sepid variables. These are pulsating stars. You can see these are pulsating stars which have a certain pulsation period. And you can use that pulsation period to actually measure the distance to those sources, because there's something called a period luminosity law. So Cepheids were discovered by Henrietta Leavitt, and so Hubble actually used distances from Cepheids law, which is Henrietta Leavitt's law. So you get the distance to the galaxy from this, and you get the velocity using Doppler effect, right? And therefore, he used the velocity which he got from the spectral lines and the distance which he got from Cepheids, and he found out this relation, which is v is equal to h naught into d, which you can see over here in these plots. If he plotted velocity versus distance, he got a linear fit. Okay, that means velocity is equal to h into d. Okay, so what he discovered is that the further galaxy is away from us, the larger is its velocity. So this galaxy is closer, the velocity is smaller. This galaxy is further, the velocity is larger, etc. So depending upon the distance the galaxy has, the velocity increases, right? And therefore, this led to a very important discovery of Hubble, which is, so I can see this again over here. If there's a spectral line which is supposed to be coming, say, in this part of the spectrum, right? Then what he actually found is, you can see the spectral line is over here. But if the source is far away from us, these are redshifts, z is equal to different values, you see that the spectral line goes shifted to the redder part of the spectrum. So you basically need to measure what is the shift in spectral line, and you can use that to find out the distance to the source, right? And the velocity, sorry, the velocity of the source. The delta lambda by lambda is equal to v by c. And therefore, he discovered he discovered what we call the idea of the expanding universe, the fact that the universe is expanding. And that leads us to our thing of why do we need to look in infrared? Because what happens is, when we are looking back in time, right? When we want to look back in time, you know that supposing you had optical light in our present universe, when it is further away from us, it gets shifted to a wavelength which is longer, which is infrared, right? It's going to longer and longer wavelengths depending upon the redshift or the distance of that object, right? So therefore, if you look at this image over here, with ground-based observatories, when we are looking only in optical wavelengths, little bit maybe in infrared, you can go into the age of the universe when the universe was only about 6 billion years, because that's the distance you can, that is the longest wavelength you can get. When Hubble Deep Field was this thing, there's a near infrared camera on Hubble, this thing, which there was the deep field as well as the ultra deep field. In that case, what happened is, we were looking at the near infrared, and therefore you could look to an earlier part of the universe when the universe was of an age of about 800 million years, right? And then you have 480 million years also with the ultra deep. Now, what happens is, with James Webb, if we observe in the infrared, we are observing in the infrared. So these are galaxies which are actually very far away from us. They are emitting in the optical, but because they are so far away from us, hence what happens is, the optical wavelength sources are now giving their light in the infrared. And therefore, now when we are looking in the infrared mirror, we are looking at much longer wavelengths than what Hubble did. So by looking at longer wavelengths, we can go to a universe which was barely 200 million years old, right? So we are actually looking at the universe when it was really, really very, very young, only of an age of 200 million years. And that's happening basically because we are looking in the infrared. And therefore, it becomes very essential for us to look at the infrared. So why do we need to look in infrared? First of all, I told you is that if you look at, see, this is the Orion Nebula. Many of you all may know Orion Nebula. And you know that this is a region of star formation. Here, this is the Orion Nebula. This is the Orion constellation. This is a region of star formation. If you look in optical light, it basically looks dark, black, because there's a lot of gas and dust over here, so you cannot see optical light. But this is an image in the infrared. If you were looking at it in the infrared, you see a lot of gas and dust over here, right? And therefore, you can study these star forming regions very nicely if you were to look in the infrared. So, if we want to study young stars, young planets, star forming regions, we have to study them in dusty regions, which are only observable in the infrared. And hence, we need to do that. Similarly, if you want to study exoplanets, right, looking for possible life, to actually look for elements for most of the spectroscopy which we need to do, most of the spectral lines lie in the infrared. They do not lie in the visible or ultraviolet. They basically lie in the infrared because the dust in the exoplanet actually absorbs the light and re emits in infrared. So we have to observe them in the infrared. Similarly, very high redshift objects, for example, objects of a very early universe, they will emit essentially in the infrared because they're at a very high redshift. So their delta lambda is very large. So even their optical light will be observable only in the infrared, right? Colder objects like debris disks and planets, they also emit in the infrared. And these infrared bands are, we cannot study it by ground based telescopes. We have to do it with space based telescopes. And Hubble cannot do it because Hubble only observes till the near infrared. It doesn't go beyond. If I want to go beyond, I have to do it with a mid infrared or a far infrared telescope, which is actually what it is for in the case of this thing. Now, James Webb can also observe opportunistic targets within 48 hours, depending if there's a sudden transient source or an interesting source. It can also look at those kind of objects. But we now understand why we need an infrared telescope. So I told you why we need a telescope, why should it be out in space, and why should it be infrared also. So if we again let's look at James Webb and compare it to Hubble. If you see, Hubble was launched in 1990, right? It's already a pretty old telescope, while James Webb got just launched 6 months back. James Webb Hubble has already been operational for 32 years. James Webb is expected to have a lifetime of 10 years. It may not exceed too much because for infrared detectors, you basically need to use cooling, okay, using cryogenic technology. And therefore, the basic lifetime of James Webb will be defined by the lifetime of the coolants. So when the coolants get over, then you are forced to actually decommission the telescope. So it depends upon how fast the coolants on the telescope actually get over. So it may slightly exceed its time, but not too much because it'll run out of its coolant material, whatever is there in that, right? So we will by then it will time out. In Hubble, we didn't have such a problem, and therefore Hubble is still operational. So, like I told you, in principle, James Webb is a Herschel complementary because it actually looks at similar wavelengths as that of it has a larger overlap with the Herschel wavelengths. Herschel is 55 to 650 micrometers, while Webb is zero point 0.6 to 28.5 micrometers, and so in that way, it's a complementary to that. So let's go on its major parts. Let's look at, for example, the mirror. Like I told you, the mirror is basically made up of 18 segments. Okay, it's what is called a honeycomb structure because you cannot have one mirror for 6.5 meters. So instead, you make 18. And the other reason why you need 18 is because you needed to fold the mirror. If you remember, I told you that when we launched James Webb, it had to be a folded telescope. So you could not have a single primary mirror of 6.5 meters diameter because it had to be folded, right? So what happens is when the mirrors were prepared, you basically needed to prepare it in such a way that the mirrors have to obviously take the effect of the launch as well as the this thing. So each segment has a size of 1.32 meters with a weight of about 20 kgs each, and what is below that is what are called accentuators. So if you look at the telescope, these are our these things. If I actually take images from it, that's the telescope. This is the secondary mirror. This is the primary mirror. Light falls, gets focused from the secondary, and you'll see one of the biggest things about the telescope, what it was doing for the last 6 months, is that each of these mirrors is going to give an image, right? But you need to align these mirrors so that all the images come to the same central point over here. Now that alignment is basically done using what is called accentuators, right? So what is there is that below each mirror there are accentuators which will actually adjust the telescope so that everything falls, everything gets aligned properly, right? To give you this thing. The other important thing is that this has to be cold, and the cold has to be minus 220 degrees centigrade. And to keep it cold, hence it was sent at a distance of 1.5 million kilometers far from the Earth and the Sun with sun shields to protect it, right? Now, so this is the primary mirror segment. You have a secondary mirror, tertiary mirror, and there's a fine steering mirror. And like I mentioned over here, when light falls onto the primary mirror, it then comes out, it gets focused with the secondary mirror, right? You can see the light path. This is the secondary mirror. And then from the secondary mirror, it goes to the tertiary mirror, right? From which it then goes to the different instruments, etc., where that it has to go to, right? So And the other important component for this is the sun shield. Like I told you, we have to protect the telescope because the telescope has to be at a very cold temperature of barely 30 degrees absolute zero. And therefore, this sun shield is basically made up of, it's as thin as a human hair. And it basically was made up of a material called polyimide film. And these are membranes which are in 5 layers. And essentially, the job is to reflect the sun's heat back into space, and therefore this thing is very very delicate, and therefore in 2018 actually there was a tear in one of the shields, and therefore remaking that thing is what led to the delay of 3 years, right, and actually making of the sun shield. So this is the sun shield, like I told you, thin as human hair in 5 layers, and it is what is essential to actually maintain the telescope at a temperature of 36 degree Kelvin, right? So you need that kind of a sun shield. Now, again, to protect, to have the infrared effect, we basically needed to send the star, the telescope far away. So, if this is the sun and this is the Earth, there are 5 points at which the gravitational force actually gets balanced. If you look at Hubble, Hubble is very, very close. It's just 570 meters above the Earth. But because James Webb was meant to look at the infrared, we had to send it further away. So it was sent to this point. This is called the L2 point, or the Lagrange point 2, where the gravitational force of the Earth and the Sun gets balanced. Okay. So if this is the Earth going around the Sun, this is the L2 point, and James Webb is actually going around the L2 point. Okay. And that's the kind of path of James Webb in its orbit. So this point is at about 1.5 million kilometers from the Earth at the Lagrange point 2. If you want to ever know where is Webb, you always have to remember that Webb is always away from the sun because it's at that Lagrange point 2. So if you were to look at this, the moon, right, the horns of the moon point away from the sun. This part points towards the sun. So this is the direction which you would actually find James Webb. So James Webb is always in the direction opposite to that of the sun. So if this is the sun, you have the James Webb positioned over here. So it is accordingly positioned so that it is all the time not facing the sun, right? The darkest part of the moon shadow will always point towards L2. Okay. The other thing is, what are the instruments on the telescope? So there is a near infrared camera, which is developed by the University of Arizona, near infrared spectrograph made by ESA. There's a MIRI instrument. Uh, the MIRI instrument is there. Then there is the Jet Propulsion Lab, as well as ESA made it. There's a flight guidance sensor, which is made up by the Canadian Space Agency. So that's the primary mirror and the different parts. So there's a lot of engineering which goes into this. So even in my last week's lecture, I spoke to students about career prospects in astronomy. One thing is doing the science of it, but there's a lot about the technology and the instruments developed in it. And this is where basically you have a lot of engineers playing a very important role in astronomy, in basically building the instruments which we use for this thing. So if you actually see, James Webb is truly an engineering feat if you see the kind of instruments that have been made on it and the way it's functioning. So it's truly an engineering wonder. This is a shorter video, but I can actually show it to you. So you can actually see there's a time-lapse video over here of how it was actually built. And you have clean rooms where you're actually building the instruments. Yeah, so here you can see this is basically work done by engineers. These are not astronomers. And this is in making of the instruments, right? So you can actually see that this is a very difficult job with which you're actually building the whole instrument, right? In setting up the mirror, the secondaries, the primaries, as well as all the instruments, etc. Then there are accentuators below each mirror to help for alignment, etc. And it's truly an engineering wonder if you actually see the way they built the telescope and all the capabilities of the telescope, right? So I'll move a little faster with this. And yeah, okay. So there are lots of these videos available on the net. You can actually have this thing. So after the telescope was actually made, it was packed up, and you're maybe aware that there was final testing done of the instruments, right? You actually had to, that's the mirror. These are the sun shields, which you can see over here, which were folded onto it when it was sent for launch, right? So you had to fold on all this stuff, And then you had the solar panels also, which had to be added. So you have to, all this has to be done in a totally foolproof way where there is no question of anything going wrong, right? It has to work correctly, right? So it was packed in this thing and actually sent by sea on a barge to South America, right? To Kuru, where that was the place where it was actually launched. So I don't, yeah, that's the barge on which it went, and it went for 16 days before it reached the point in the Kuru River where you had the launch taking place, right? And after it got launched, it actually took 6 months. So what you have is you have the launch taking place. First of all, you have the solar arrays opening up. Then you have the sun shields opening up. Then you had the primary mirror opening up after 9 days, secondary mirror, and then it moved to L2. It took a month to actually reach L2, right? And so before it reached L2, the sun shield had to open. The 18 segments, they all had different images, and all the thing had to, be assembled. And then the deployment process is something like this. It'll open in browser. I hope you can. Okay, it's not coming in browser, so we'll just close it. Yeah. So let's go next. And this was the last shot that people had of the James Webb, right? While it actually drifted away, right? For its month-long journey. Now, the first image that was given with the James Webb was one which basically, like I told you, all the 18 segments are going to give you images in different points. So this is an image taken by a 25-hour exposure, right? Where you can see that the images were totally aligned in all random directions and they had to be aligned. So the accentuators have to be used. And this whole period of 4 or 5 months was used for alignment of the telescope as well as cooling of the instruments and the telescope. So the mirror alignment had to take place. So these are these accentuators which are there below each mirror. Now they have to adjust so that you can adjust it to get the right curvature of the telescope so that they can actually add up to give you your image. So this is what is the process of mirror alignment. And mirror alignment has taken almost 4 months, right, for that to take place. And that's what you can see over here. Now, the early science programs was study of exoplanets, stars, galaxies, dark matter, etc. So I'm going to now very fast show you the early science programs. These were the 5 images which were planned, which James Webb would give people of their first view of the universe with James Webb. And I'm going to tell you about each of them. So the first image it was released, this was released one day before the actual release was 12th of June. On the 11th of June, the President of America, Joe Biden actually released this image. This image is actually of a galaxy cluster, S-Max, which is at a distance of about 4.6 billion years. And this image, believe it or not, it is supposed to be the patch of sky if you had a grain of sand, which you held at arm's length, right? And this is about that is the field of view which you are looking at in this. And this was obviously it was a blank field of view, but you can see that now when you look through the telescope, the number of galaxies you actually see, it's like full of galaxies. So this was taken using the near infrared camera, the NIRCam, and it had an exposure of about 12 and a half hours. So what you can see very interesting in this image is these arcs, okay? And these arcs are formed by what we call gravitational lenses. So let us see what are gravitational lenses. You all know about normal lenses. Normal lenses basically are made up of glass, and when light passes through the glass, the light gets bent because of refraction with the glass, and that is why you get images, right, from the glass, like which you see with your spectacles or with whatever. Now, in the case of gravity, we know that gravity is such that if you have a massive object, it can actually bend light, okay? Just like a lens, like a glass lens. The glass lens does it because the difference in refractive index, there's a difference in the velocity. Similarly, exactly the same way, a massive galaxy or a massive object can actually bend light. And when it bends light, it actually causes it to give a lensed image. And that's when, for example, if I'm looking at this galaxy over here and there's this massive thing before, I'm going to actually see some lensed pattern. So that's what's actually happening in this case. You can see these orange arcs. These orange arcs are essentially the same galaxy, but you're seeing multiple images of the same galaxy because this whole region over here is so massive that light coming from behind See, this is a red thing. That means this is a red galaxy. This is a reddened galaxy. This is at a higher redshift. In this image, the simple way to know what is close by and what is far away is the redder the object, the further it is away from us. The bluer it is, the closer it is. So these blue objects which you see are essentially stars, right? But these redder ones which you're seeing are basically galaxies. The redder they are further away from us. Now, this galaxy cluster is comparatively closer to us. So it's the massive one which is bending the light. And the galaxy, this red galaxy which is getting lensed, is something way behind. And that's why it's giving us these multiple images which are in the form of arcs. Okay. And therefore, this gravitational lens effect which you're getting, you see, this is also beautiful lens effect. You see this smiley. This is the same galaxy which is giving these different arcs because of the presence of mass in front of it, right? So similarly over here, you could have images of a quasar which is getting lensed or galaxies which are getting lensed. And that field essentially has a whole set of lensed galaxies. The other thing which you see in this field is that all these galaxies are obviously at different redshifts, right? They are all at different redshifts in this image. And therefore, based on that, the first paper that could come up was a paper which came out, which was literally a week from the time that came out. Was this paper was actually for this image. If you actually see, these are the galaxies, and based on this, you have different redshifts, right? So the blue ones are within redshift 1.5 to 3, green is between 3 to 4, and red is between 4 to 6. And therefore, you had the first paper which actually came out where they actually studied the morphology and structural parameters of galaxies seen in that first image for galaxies with redshifts greater than zero point 0.3. Now, the galaxy cluster is very close by. I told you it's only at a redshift of 0.39. It's very close by. But there are a whole bunch of these galaxies at redshifts larger. So they specifically looked at the galaxies at redshifts larger than 3. And what they found was very, very interesting. It is assumed that in the earlier universe, there must have been lots of mergers and lots of activity between galaxies, right? So basically, the idea was to look for galaxies in larger redshifts. And they actually found that redshifts greater than 1.5, the bulk of the galaxies are disk galaxies. They dominate over the overall fraction. This is something very interesting because you can see over here with redshifts, this is the distribution of spheroids, of disks, and peculiars. So you see that typically disk galaxies are peaking, they are larger. And that basically tells you that galaxy structure, it formed much earlier than previously thought. People thought that the early universe must be more full of, peculiar galaxies or galaxies which are not yet formed with proper shapes. They would be irregular, peculiar, interacting kind of galaxies. But here we can see is that in this field, for galaxies larger than 1.5 redshift, the bulk of them are disks, right? And for example, what these authors use is they use something called an asymmetry concentration index as well as the Cercic index. We don't have time to talk about it, but these are basically parameters with which we quantify the morphology of galaxies. And basically, what they found, like I told you, is that galaxy structure seems to have formed much earlier than previously thought, right? Compared to what we actually thought, we do have galaxy structure forming much earlier. So if you even see Cercic index, you have these kind of Cercic index. The disks are the ones which have Cercic index 1, right? So you have disks over here with redshift. These are other kind of galaxies. The other object which was observed on 12th July, which was released, the next interesting object was what is called the Stephan's Quintet. And Stephan's Quintet is actually a visual grouping of 5 galaxies, of which only 4 are actually related. And this was actually a very large image. It's about one-fifth the moon's diameter. The moon's diameter is half a degree. So this is one-fifth of that. And it contains over 150 million pixels. And basically, this was to look at a set of interacting galaxies. And what they found is that these are the galaxies which make up Stephan's Quintet. And this galaxy 7320, NGC 7320, actually, this is the brightest member, but this is not part of the true group. Okay. It has intensive H2 regions, etc. This is not part of the group. The group are the other 4 galaxies. Okay. And what was done is that basically using the MIRI detector, what they did is they actually measured the velocity of gas. Now, you know that this galaxy basically, these galaxies have an active galactic nuclei, there's black hole sitting over there, and therefore there's gas going into the black hole, okay, in this region. And therefore, you can see it over here. And therefore, what was done is spectroscopy was used to measure the speed at which this gas is going in. And therefore, if you see the blue clouded regions are the ones towards us. This is the region going away from us, again in neon atoms as well as in molecular hydrogen. And therefore, with this, they could actually measure the velocity of gas near the active black hole. Similarly, even the composition of gas, the idea was to study what is the gas over here. So they found atomic hydrogen at 0.65 microns, iron at 1.64 microns, atomic hydrogen at 1.87 microns, and molecular hydrogen at 4.7 microns. And therefore, this was done using what are called integral field units. And they basically measured the bright emission from outflows of hot gas near the so this is where the active black hole is, and they actually measured these quantities. The MIRI detector, like I said, it actually gave us the spectrum of the sources. So what you have over here is that so you have a wind over here, which is this smaller circle, and here's the black hole part, and you actually have a top spectrum which shows hot ionized gases. These are the hot ionized gases: iron, argon, neon, sulfur, oxygen. And the bottom spectrum shows that the black hole has a reservoir of colder, denser gas also, and that's what actually feeding the black holes in this object, which is so far away. The next interesting image which was given, which was that of NGC 3132, which is called the Southern Ring Nebula. And this was actually observed with the thing called near infrared camera as well as the MIRI camera. Now, this is actually, I've left a quote, some stars save the best for last. This is actually showing the end stage of the life of a star. So, typically, a star like the sun, this is a sun like star, typically a star like the sun, when it finishes fusing all its hydrogen, it's going to throw out all shells of material in outer space. And what would be left instead would just be the white dwarf, which is, which is just the core of the star. So if you look at this near camera, this is the star, but this is not the star which has caused this nebula. There's basically a binary system which you can see here in this MIRI image. This is the mid-infrared image. You can see two stars, and here you can see it's here, and the second star is somewhere here. 8 o'clock position on the diffraction spike is the second star. Okay, here's the second star, and basically the smaller, fainter star is the one which has actually caused this. This is called a planetary nebula. Okay, wrongly called. It was assumed that this is where planets are formed, which is absolutely wrong. This is actually the end stage of the life of a star. But this small star is the one which actually caused it. It's part of a binary system. This one has not yet, this is still a main sequence star. This one is a white dwarf, right? So in this image, you can see both. In this one, you can see only one. And you can see both in this because this is seeing through the dust. That's why you can see this over here. So if you look over here, this is an image of stellar evolution. If you have stars forming from a giant molecular cloud, if it's a star like the sun, it becomes a main sequence star, after which it will become a red giant. It will throw out all its outermost shells and then become a white dwarf, right? And we are seeing this object in this stage. This is the stage which is the planetary nebula stage, which is this stage for the Southern Ring Nebula. So the Southern Ring Nebula is in the planetary nebula stage, which is over here, which is the future of sun-like stars. So our sun will also end up something like this, to be a red giant, give the planetary nebula and the white dwarf. But if the star is a much more massive star, a high mass star, then it will become a supernova, right? There'll be an explosive event. And depending on its mass, if it's a lower mass, it will become a pulsar or a neutron star. If it's higher mass, it will become a black hole. So this image was a reflection of the future or the death of stars. How do stars die and what happens in their later stage of evolution? Now, planetary nebulae, they don't last for too long. They actually last for 600, for a few thousands of years. This one is relatively close to us. It's only at 613 parsecs. And like I told you, it's made up of two stars, a white dwarf and other main sequence stars. And this is how the shells are basically thrown from the star. So it is this thing that you can see the shells. You can see 1, 2, 3, 4, 5, 6. So it is that there are approximately at least 6 shells, right? This star has ejected at least, 8 shells. The star has ejected at least 8 shells of material out into this matter. Now, in this image, it's interesting to note that one is the image of the nebula, but along with the nebula, there's still more information. For example, in this image, look at this over here. This is a galaxy. Okay, this is an edge-on galaxy which is very, very far away, and people are actually working on this particular edge-on galaxy, which is at a very large redshift. and sitting in the background of this image. So some of these images, this is typically what happens even with Hubble images, that with Hubble images also, if you access it from the archival data, often people may have used it for a certain purpose, but in that very image, there could be some objects which could be of interest to you, which are actually not related to the object at all. Like, for example, this galaxy has got nothing to do with this planetary nebula, but it's a very interesting object which is observable using this, right? Now the other figure we got from this is the Kareena Nebula. So now we've gone to the death of stars. We are kind of going reverse. So we started off with the speck of sand size of universe. Then we took Stephen's Quintet. Then we took Southern Ring Nebula, and then we come to Kareena Nebula. This is a region where very young stars are being born. Okay, so these are called stellar nurseries. It's also NGC 3324, and young stars are born over here. And what you can see is that there are huge pillars over here, right? And you can see that as the stars are born, there is steam that actually seems to rise out. There is steam coming out, and it rises from the mountains. It's actually hot ionized gas. I hope you can see it over here. This is hot ionized gas which is coming out from the nebula because of radiation. Now, this work could only have been done like this with James Webb, because this is a very dusty region. You cannot see through it much in Hubble. I'll show you an example of that. And here you're getting to see objects in the earliest phases of star formation, which otherwise you could not do it. So there are various important questions, open questions in this. For example, some of these stars actually have jets, right? If you zoom into this, you'll actually see some of these stars having jets. Seen some jets, but if you actually closely look there, you'll actually get them. So some of them actually have jets, and these are very, very young stars. They are in the earliest phases of star formation, and therefore this kind of an image would give you very good insight into the star formation process. How does it proceed? Where are there is even there's a cavity over there, so you can see where are the ionized rim, that ionized rim which you can see, which is that boundary part, right? This is the ionized rim, and you can actually see the distribution of stars along the rim, right? How are they distributed along the rim? And for example, you can see if how would increased pressure actually trigger material to form into new stars? What determines the number of stars that form in a certain region? Why do stars form with a certain mass? And these are the kind of questions we would like to answer with these kind of images, right? The last image actually is not an image, it is just a graph. It is a graph of the spectrum of an exoplanet. This is an exoplanet called WASP 96b, and you have an instrument called the Near Infrared Imager and slit the spectrograph. This was actually used to look at this exoplanet. It actually is around a sun-like star at a distance of about 1,000 light years away, and it completes an orbit in less than 3.5 days. And therefore, what they did is they observed it for about 6 hours, 23 minutes, 2.5 hours before the transit. So this is the star. The planet comes in the front and goes away, right? So if you want the spectrum of it, what you do is you actually take it before the transit. So they first took the images before the transit, and then after the transit and during the transit. So what you can do is using that you can actually get it. Now remember that with these exoplanets, since the planet is very small compared to the star, what you have is that this dip is barely a 1% dip, right? It's barely a 1.5% dimming. So you need a very sensitive instrument to actually measure this dimming and actually look at the transit. And when they looked at the transit, they actually got this spectrum. And this is really very interesting because the last image is this graph, and the spectrum actually shows you water, right? So you're actually detecting water on this exoplanet using James Webb. So that is again one of the important tasks of James Webb, is that for the exoplanets, which are candidates from Kepler, from TESS, from various other missions, James Webb can actually look at targeted exoplanets and try to characterize their atmosphere. By characterize the atmosphere, that means to basically find out what is the atmosphere made up, because we want to know whether the atmosphere is made up of, water, carbon dioxide, oxygen, whatever. We want to know the composition, right? So that is the last image. So what we've actually, these 5 images were just the beginning. It's just going to show you what are the kind of things we're going to expect from James Webb. So this is a comparison of Southern Ring Nebula. This is the Hubble image, and this is the image with James Webb. Similarly, Kareena Nebula with Hubble, you can see you can hardly see anything because there's lots of gas and dust there. But with James Webb, you can see a lot. And James Webb has all these instruments on it, and from which we're really expecting very, very interesting results. I could not help myself from showing you some nice memes on what are, people are really going, really, fascinated by the kind of science we get from it. Like there's one meme which actually says, this is Southern Ring Nebula with a smiley face, identifying intelligent life. There is one where, this is the difference between the Hubble image and the James Webb image of the sky. And then you have this other one also. So there's a lot of activity on regarding James Webb. But obviously, this is not what one expects, right? This is also one of the other jokes which has gone quite viral on the web, where people expect that this was Hubble, this is what James Webb is going to give you. It's not going to give you this. It's basically going to give you what I showed you in the other image, right? This is the kind of precision we are expecting from James Webb. So I'm sorry I slightly overshot, but just that this topic is so very interesting and there's so much to say about it. So there's now a lot we're expecting from James Webb. Along with that, in 2027, there's the Nancy Roman telescope, which is going to go. There's the Euclid telescope, and there's also the Super Hubble. There's also another telescope in the pipeline, which is expected in the 2040s, which would then be the true successor to Hubble, which would do on Hubble wavelengths, which is expected to be launched in 2040. So thank you. I'll end with this, and I'd be happy to take questions.
Thank you so much, ma'am. It was such an illustrative presentation and also give us a very comparative clarification on all the telescope and also the future coming projects. So now we are open for the questions and doubts. If anyone would like to even comment on that, you can drop your question in the chat box and I will be highlighting those so that it comes on the screen and ma'am can also take that. You can drop in the chat. I'll be highlighting those.
Yeah.
So meanwhile, people are writing. I can definitely show ma'am a great initiative and well amazing opportunity for all of us.
Yeah, I should
And
also mention that, for example, for most space telescope data, obviously this is excellent data, and you would obviously ask the question is that, am I ever going to be able to analyze data of this kind, right? Then just for your information, for example, Hubble data is freely available on the net. What is done with space telescopes is that people write proposals for the data, and for some period, for a year or 6 months, the data is proprietary data, which is only their data, right? But after that proprietary period, the data is available freely for anybody to use for analysis. Similarly, all these first image data of James Webb is already available on the net. So that's why the paper which I showed you, right, which came out a week after the data came out, that's basically using the data because it's already available on the internet. So James Webb, what happens is that if people write proposals, right, then for a certain period, the data is only theirs. Nobody else can get that data. Only they will get it. But after a certain period, it will be available to everyone. And other than that, there could be certain sets of data, like it is there with with Hubble also, that sometimes there could be a kind of a survey data or legacy project or something like that, where from the very beginning people observe and the data is available online for everyone, right? So it's all, like I said, it's already available. All these 5 images which I showed you, the complete FITS files, all the data is already available on the internet. You can start practicing, you can start working on that data. It's already there. And as time flows, different sets of data will be available off and on, right? So agreed, it is very, very difficult to get time on James Webb. If you were to write a proposal to observe something on James Webb, it's obviously very, very difficult to get it, very competitive. But there is a lot of data which will be available freely to everybody, right? So you can anyway do some science with that data, and that may help you to write your proposal when you want to do something else with it, right? So you can, for example, in your proposal show how using available data, you supposing you were studying some galaxy, right? And you took down that data, you studied the galaxy, you got some results. Then you on based on that, you can write another proposal that, like, I studied this galaxy. I want to study some other galaxies to get, some other results, whatever. So please remember that this data is going to be available for everybody. uh, After a certain period it will be there for everybody, and in the beginning also you will get some amount of data. So be on the lookout, check up, try to download. You do get the data, and you can plan some kind of projects or some kind of work with that data, because it's excellent quality data. You can't get better data than that. That's the best thing about Hubble and James data, the web data. Yeah.
So with that, we'll take one question in the chat box. But before that, many of the thank yous.
Yeah,
That very new thing. Thank you, ma'am. It was excellent. And with this, we'll
welcome.
take this question. Can Webb tell us about the question whether there is life out there?
Yeah. So, like I said, right, web is basically designed around origins. And one of the basic interesting questions for everybody is the origin of life. And about life out there is kind of difficult to say. But for example, like I showed you the spectrum which they have for that exoplanet, where it shows water. So, what we can do is we can look for indicators of life. For example, if we assume that habitability, right, for exoplanets is the points at which water is in liquid form. So, for example, if you have an exoplanet which is in the habitability zone, and then you do the spectroscopy with which you find out that it has, amino acids, it has water on it. In that way, you can characterize and get it. Confirming life as life is difficult, but you can look for indicators, right? These are called biomarkers. You can look for indicators of life and check for them. Contacting that life and verifying and all, that's yet another problem, right? But with this, we are the stage at which we are now is we are still identifying exoplanets, right, using Kepler and test data. Now with telescopes like this, with bigger ones, we can characterize those exoplanets, like say what is the atmosphere made up of and things like that. Later on, the next stage will be actually like, checking if there is life in that habitable. You can have a habitable planet, right, which need not have life. So that is yet another stage which will come in the future. Yeah.
Any other questions? Because I can see lots of thank yous. No new questions are
Yeah,
popping
yeah.
up.
Please ask questions.
So, ma'am, is there any ongoing project in any college or maybe any organization are hosting such project-based learning where like enthusiasts or people who are interested in astronomy can take further step ahead, as you told that data is available on online or something, or maybe citizen science projects or something.
Actually, we ourselves have been doing a lot of that over this COVID period. All we did a lot of it with various data sets. Online also, you can find a lot. For example, if you want to analyze Hubble data or Kepler data, test data, there's a lot of resources available online. Most of them you go to their own websites. Many of them have tutorials and things like that. We had done a lot of that during COVID times because we had a lot of students who worked on projects. So actually, I think you just have to search on the net. You need to search online. So yes, but there are many, many people working on things like that. There's a lot in that.
Because this was one of the questions, because students kept on asking when they come to the planetarium, like any project we can suggest them, what are the things or what are the organization which are offering such projects in which they can
Yeah.
contribute or they can learn.
Yeah, and then obviously the important thing is the level. The citizen science ones are good for people who do not have a science background, etc. But for example, if these are university students and all, then they may do actual coding. They need to do some coding and do something like that. So, yes.
So
Okay.
next question, Vandana Singh, how far back in time is Webb expected to see?
Yeah, so like I showed you in the plot, the universe is 13.7 billion years ago old, right? So this is supposed to look at an age of 200 million years. So you're going to go back like 13.5 billion times. That's what's expected. So you're obviously not going to the point of t equal to zero. T equal to zero is obviously not doable, but this is very, very close to that, quite close to that.
So any other question? I think in your presentation, ma'am, you have explained in such a good manner. I think most of the people are like observing those information, and it will take time to think and
Yeah,
then analyze. Then we can have certainly can plan some other session in which we can just take those questions,
yeah,
because
yeah.
I'm
That
also
should
just
be it.
exploring that part, because all the information was such fascinating, and we as an enthusiast and people who are interested do take time to absorb all those information to
That's right.
arouse their curiosity to ask questions.
That's right. Yeah. Hmm.
So the infrared light which JWST is capturing was in optical range, and what about the infrared emitted in first place?
Yeah, so I see like what I told you is that because of the redshift, right? Because what we redshift basically mean is that light is moving towards the redder direction when the universe is expanding, right? And that is why what I was saying is that what was originally emitted by an object in optical, right? It moves to longer wavelengths. It is infrared or even longer or wherever, right? Depending upon what is the redshift of the object. So, depending on the redshift of the object, JW, supposing it's doing it in Kareena Nebula. Kareena Nebula is very, very close by. So, if in Kareena is seeing infrared, that is originally also infrared only because that is very close by. Kareena Nebula is not at all far from us. It is in our galaxy very close by. Similarly, if we are looking at that exoplanet or we are looking at even that southern ring nebula, what you are seeing in infrared is pure infrared light, right? But for example, if you're looking at the images, for example, in that in that Stephen's quintet, or even in the earlier the galaxy field which I showed you, right, in the X-max field, in that case, yes, in that case, if the galaxy is very, very far away, if it's redder in light, most probably it has emitted in optical light, but because it's so far away, we are seeing it in redder light. So that is for those galaxy clusters and all that. But for example, like I told you, Kareena Nebula, Southern Ring Nebula, WASP 96b, what is infrared only because it's very close by. It's local universe. It's not so far to have gone to redshifted. The redshift is close to zero. It has no redshift, so it is fine. It is infrared light, right? Uh, the other question is, what about infrared emitted in first place? That will go to yet longer wavelengths. So if you look at still longer wavelengths, that is, for example, in the radio, people do that. They observe in radio wavelengths, then it goes to larger wavelengths, right? So if you're looking at very high redshift objects, their infrared will then go into radio side, into longer wavelengths, towards that side, right? But zero redshift objects, things were within our galaxy, what is infrared is infrared. It's as it is.
So no new question, ma'am, in the chat room, in chat box. So I think take a wrap
Yeah.
with this. And thank you everyone for coming
Yeah.
online, giving your precious time. And also Priya ma'am for giving your precious time and sharing such a brilliant presentation on such a buzzing topic about the James Webb Space Telescope. And this video will be available on the Planetarium YouTube channel for further references if anyone would like to see. And we will definitely come with some new topic in the coming times. Thank you so much, ma'am. Again, thank you so much
Thanks a lot.
for talking to
Thank
us.
you.
Thank you.
Bye bye.